Okay, hello everyone. Hope you can hear me. So my name is Ricardo Macedo from INESC, and it is my pleasure to host the final session of the joint webinar series between BigHPC project and the UT Austin Portugal Program. For this final session, we have a wonderful set of speakers, and I would like to give a warm welcome to Bruno Antunes from Wavecom, João Paulo from INESC, João Cazes from TACC, and Samuel Bernardo from LIP. So for more speakers, first, Bruno Antunes is a research manager and product developer for Wavecom. He obtained the electrical and computer engineering degree, 5 years of bachelor's from the University of Coimbra. And he concluded the curricular component of computer networks and communication services, master's from the University of Minho, with the outcome of his master thesis, modular platform for wireless communications, based on open source software. And this has led to the launch of Wavecom's multi-radio platform. And is currently attending the PhD in MAP doctoral program in telecommunications. Next, we have João Paulo, he is currently an invited professor and assistant researcher at INESC and University of Minho. And he has obtained a PhD degree in computer science from the MAPI doctoral program in computer science. João is currently working on large-scale distributed systems with an emphasis on storage and database system scalability, performance, security, and dependability. Next, we have João Cazes, which joined TACC in March 2005. Prior to TACC, he served as outreach lead to Naval Oceanographic Office Major Shared Resource Center, US for the Lockheed Martin. Currently serves as the director of the High Performance Computing Group at TACC, and he has over 20 years of experience in high performance computing in public and private industry. Finally, we have Samuel Bernardo, which is a software engineer at the Laboratório de Instrumentação e Física Experimental de Partículas, LIP, in Portugal. He graduated from Lisbon University with a degree in computer science and engineering, and Samuel is finishing his master dissertation. Currently working on the BigHPC and SQAS platforms development and in several national and European projects. And Samuel is also an open source contributor for several years supporting the community and free software. So next, I would like to inform you that you can and should interact with us during the presentation. And to do so, you can use the chat to share your questions. And during the presentation, there will be no discussion moments, but at the end of the webinar, we will provide you some minutes to discuss all of your questions and interact directly with the speakers. I will be monitoring the chat activity regularly, ensuring that all questions are dealt with by the speaker and at the right time. Now we can move to the actual interesting presentation. So I kindly ask our speakers to share the screen in order to kick the things off. And I think it is Bruno. Bruno, the screen is yours.
Okay. This one. Okay, just please confirm me that you can see my screen.
Yes.
Yes. Okay. So, hello everyone. The goal for today's webinar is to give you an overview of the BigHPC project development along the past 3 years and also some of its major outcomes. We are going to start on what was the motivation for creating such a project. Then we will discuss the implemented architecture, the role of the 3 developed components, monitoring, virtualization, and storage components. Then the platform integration, and finally the main results and takeaways. So challenge and goals. 3 years ago, the BigHPC project was started with the ambition to provide better support for the increasing usage of artificial intelligence and machine learning workloads in HPC centers. One critical challenge for these workloads is to efficiently manage the available resources, since typically these applications are very storage intensive, and this in opposite to the typical scientific workloads that run on HPC resources. Another important point is to make HPC more transparent to non-experts coming from the ML/AI world who are not used to this type of environments, and also to be able to isolate each application from each other, allowing for fairness allocation between them. For this, the BigHPC project developed a novel management framework for big data and parallel computing workloads. So, 3 goals were set for the development of the BigHPC project. 1, develop a monitoring solution that will be able to monitor different HPC infrastructure. 2, improve a big data application development and better management of HPC computational resources. And 3, also to improve the storage performance and management for HPC services. Regarding BigHPC overview and architecture, the BigHPC project intended to solve the identified challenge and also the proposed goals, resourcing to 3 main components, as you can see here on the picture. A virtualization manager responsible for store, curate, and manage the container files to deploy, and also responsible to launching them in the cluster if there are available resources. A store manager here that will keep track of I/O requests made to the shared resources, for example, the shared parallel file system, and also enforce the QoS policies to improve I/O performance for the application using such resources. And in the bottom, the monitor backend that will inform both the storage manager and the virtual manager of the cluster status and workloads in real time, while also storing data from the workloads run for later analysis. Here we can see the detail of the 3 of the different components. Users and sysadmins are intending to interact with the virtualization manager, either to launch their workloads or to upload a new container with a desired job. The usage of a containerized solution is of key importance, since it will allow a more straightforward path from the user's machine to the HPC center. The virtualization manager then launches the containerized workloads on the compute nodes, while the storage manager ensures the desired QoS policies from the I/O requests being issued by these containers to see if it's applied. This is also crucial since big data workloads are storage bound. The monitoring backend has access to the compute nodes and storage nodes via the InfiniBand network, and by that it can capture the desired metrics. These metrics are then fed to the users and system admins and can be queried by the virtualization manager and the storage manager. We are now going to see in more detail the purpose of each component. Starting by the monitoring component. We can see here a general overview of all the items that compose the monitoring solution. For a more in-depth overview of each component, the viewers can see the webinar 5 from this series, Monitoring in BigHPC Lessons Learned. For the monitoring architecture, and since the project is leveraging on container technology, we also resorted to containers. That was an easy solution. Actor is the monitoring probe and metric transformer that runs inside the Singularity environment inside the compute nodes. And in an external machine, Monica, the architecture for monitoring, that it's composed by the VM agent, PromScale, and Grafana. The workload can be detailed as Actor starts by collecting metrics from the compute node. The metrics are transformed into a Prometheus compatible storage and then pushed from the compute node onto the external machine where the Monica architecture is running. These metrics arrive at the port in the external machine that the VM agent is listening, and from there the metrics are aggregated and written into PromScale if the connection is available. When the metrics arrive at the database, they are then queried by Grafana in order to plot the necessary visualizations for the monitoring of the job status. So while Actor is responsible for what happens inside the compute nodes, Monica is responsible for what happens outside. So Actor is responsible for metric extraction and transformation, while Monica is responsible for aggregation, storage, visualizations, and data processing. These 2 models were validated and allow for an in-depth monitoring of the state of multiple compute nodes in real time. The monitoring backend is capable of compute metrics separated either by job and node. The job metrics offer a detailed look into the job state and are targeted to the HPC users, while the node metrics offer a general overview of the state of the node and are tailored to system administrators. This component is capable of monitoring under the nodes associated to the same job. Currently, the following matters are captured: disk, CPU, memory, process, network, GPU, cluster, and InfiniBand. As we discussed in the previous slide, these metrics are pushed from the node to the middle agent, and this is for security reasons, since the number of exposed ports on compute nodes in the HPC center is often limited, and it's not the best practice to pull the metrics from the node. That's why we use the push version. The metrics can be visualized in real time, and this is important, on the Grafana dashboard, so there is no need to wait for its conclusion. After the monitoring probe inside the compute nodes has a low overhead and does not impact on the nodes, so on the running workload. So the actor does not have impact on the running workload. The monitoring sampling rate can be configured as needed, with current the default for 20 seconds. For long-term metric storage, the database is downsampled periodically to exclude repeated data and then to downsize the size of the database. All the components of the monitoring backend are deployed in containers. Both Hector and Monica use a container architecture. So some examples of the visualizations that were gathered in this job. Why Grafana? The use of Grafana as a visualization solution is manifold. We think it's widely used, is open source, can generate powerful visualizations, and also users who have previous experience can feel right at home, taking full advantage of the dashboards. The captured metrics can be visualized by job here on the dashboard, and we can see if the jobs is running or concluded. In this example, all jobs are concluded. The jobs can then be filtered by ID to detail the captured metrics. In this example, we can see, for example, dashboards for CPU, memory, network, disk operations, GPU metrics, InfiniBand, and cluster metrics. We can also fine-tune the dashboards. So for everyone that it's used to Grafana, we can fine-tune these timestamps. And the time series graphs can also be open to show a more detailed of the target metric. For example, here we can see the GPU temperature while performing some GPU-related operation. So I think we can now get back to the virtualization manager. So John, the stage is yours, please.
All right, I had to unmute. Hello.
Hi, we can hear you. At least I can hear you, John.
And it's like before, I had no controls. So I'm gonna discuss the virtualization manager. So this is the piece that sort of ties everything together, and it's the first piece the users will see when they go to submit a job. It's based on a command line interface, so it's sort of similar to logging into any regular HPC system and submitting a job. The difference is the virtualization manager acts as sort of a meta scheduler and an orchestrator, in that it's possible that your workload can be submitted to multiple HPC platforms, and this is why we have the use of containers, right? So we can easily deploy the appropriate container to the right platform. And so what the virtualization manager does is it looks at your request and decides where to deploy the container for the appropriate platform. And then once it deploys the container, it initiates the storage and the monitoring functions. Okay. Here's a diagram of how this looks. So you have the end user logging into the interface for the virtualization manager. They submit whatever workflow they want. The request goes on the administrator side. It decides which container for the repository needs to be loaded, where it's going to go, which HPC resources requested is most appropriate. It will start the container and the workflow remotely. It will also implement the monitoring component and the storage daemons. And we just heard about the monitoring component and how the user can follow what their job is doing. And for the storage manager, we'll talk about that next. And the storage manager controls access to the storage because, as Bruno mentioned, especially for machine learning, the access can be very intensive, and without some sort of controls, quality of service, you can easily knock over a file system. And so that is to protect the system from the user. And the monitoring component gives the user an idea of how well it executed across various different platforms. So what the scheduler does, it looks at the workload, looks to see if there's a space on the available HPC resources, and figures out where it can fit it in. So currently, the only scheduling algorithms we have implemented are FairShare and FIFO. FIFO is first in, first out. FairShare is just an algorithm that looks at how often you've run. If you run a lot recently, then your priority is lower. If you haven't run in a few weeks, your priority is higher. Now, all of this can be adjusted so the admins can add their own algorithms and say, give certain groups priority or give certain workloads priority. And what we just have is a screenshot of that. I'm sorry, you can't read that, but basically this is all command line, and it's just an idea of what's running in the background. And so the repository, this is sort of where the power of this technique resides. We have multiple containers for different workloads and different applications. And as Bruno mentioned earlier, we want to make it as easy as possible for the user to say run in different sites, run different workloads, machine learning or HPC workloads. And the idea is these containers are pre-set up. They're configured, they're optimized. We've already got the hooks in for performance monitoring. So the user can get up to speed very quickly using the virtualization manager to submit the workload, using the monitoring tools to see how well it's run. And hopefully on the IO side that we're using the parallel file systems efficiently and we're getting work done without impacting the other users. Okay, now I think we're going to move on to software-defined storage.
Okay, so I'm going to talk now about the storage component, the third component of the BigHPC project. And as Bruno was saying, the goal of this component is, or the main goal is to improve storage performance and the management of storage resources at HPC clusters. And with this goal, we hope to ensure better quality of service for IO-intensive applications and jobs. And we have been talking about this. So both scientific jobs that need to access and store a lot of data, but also new big data applications such as AI frameworks and analytical engines. And besides this, what our component also aims at achieving is to alleviate the IO pressure that is jobs do over shared storage resources. For instance, the shared parallel file system, such as Lustre or BGFS. And this is very important because we know that these kind of applications, if they stress these shared file systems, they can break this and the whole cluster can become unavailable. And the solution we proposed has three main requirements, and the requirements are: first, we want to target both types of workloads, big data and scientific, but we want this solution to be transparent to applications. So we don't want users to need to change their applications when using our storage solution. And also, we don't want to change the storage resources or the software managing storage at HPC centers. So we don't want to change Lustre or BGFS. These are highly complex systems with lots of optimizations, and we don't want to make changes to these and break some of these optimizations. And so the solution we propose, it's based on well-known paradigm called software-defined storage, and it's divided into two main planes. One, it's the data plane. The data plane is responsible for managing the I/O requests of applications, and I'll talk a bit about this in the next slide. And then we have a control plane that orchestrates this data plane and ensures these quality of service policies across the whole cluster, the HPC cluster. Now, moving to the data plane. The data plane, so it's the main function is to implement storage optimizations. So we implement optimizations such as rate limiting. We can rate limit the number of I/O operations a given application is doing if this application is, for instance, stressing a lot the parallel file system. But it can also be used for other type of optimizations, for instance, caching. So we can bring data closer to the application to memory or local storage so that this application can access this data faster. We can implement optimizations such as tiering to take advantage of the different storage resources that exist in HPC clusters. And besides this, the data plane we are proposing also is programmable in the sense that we need to be able to optimize or to develop these optimizations, but also to propose new ones. And as I was saying previously, it needs to be generally applicable. And this means these optimizations need to work for different applications, scientific applications, machine learning framework applications or workloads, deep learning workloads, and so on. And how does this data plane works? Well, it's divided into stages. These stages basically are intercept. So there's one stage per application. Remember that I'm talking about application, but it's the same. It's similar to job. Okay, so we have one data plane stage per application or job. These stages intercept I/O requests from applications, and the stages have some key features. One of them is the stages need to be able to differentiate different types of I/O. So differentiate between data, metadata requests, even specific types of metadata requests, for instance, open calls, closed calls, for data writes and reads. And we need this differentiation because we want to ensure policies that are very specific. So we may want to only limit metadata requests because we know that this type of requests are the ones that typically are more stressful or harmful for the shared parallel file systems. Then, as another feature, this stage needs to be able to enforce some rules, and the rules can be as simple as I need to rate limit the requests of this application, metadata requests of this application to a certain amount of operations per second. Otherwise, I may be compromising the quality of service of other applications or the quality of service specified for the specific application being targeted by this stage. And the stage also needs to collect metrics from the application. So the stage is intercepting I/O requests, so knows what application is issuing in terms of I/O requests, and send these metrics to a control plane. I'm going to talk about this in the next slide. And the control plane is the one that will receive these metrics, do some calculations, and send the enforcement rules to the stage, and that will apply this through the I/O enforcement mechanism. For the data plane, in the project, we provide two prototypes, PIO, which is a library for building custom data plane stages. And then we provide Paddle, which is a data plane for HPC storage systems that is built with the PIO library. Now, the data plane is very good at managing and handling the I/O requests of a given application. These applications can be running on different compute nodes, as shown in this image. But the problem is that all these, for instance, in this image, there are 3 jobs, there are several compute nodes, and there's one data plane stage per compute node, but all these compute nodes and these jobs are accessing the shared parallel file system. And if we want to avoid, for instance, saturating this shared resource, we cannot do this without a coordination of these data plane stages. So each stage knows how to handle IO requests individually for an application, but does not know the overall status of the HPC cluster, and in this case, for the requests being submitted to the parallel file system. And this is where the control plane enters. And the goal of the control plane is to ensure quality of service policies at the HPC infrastructure. These policies can be specified per job, per user, or jobs of a user or a group of users, and can also be specified cluster-wide. And again, why do we need to differentiate requests at the data plane stages? Because we can also have QoS policies that target a specific type of requests. Again, as example, data versus metadata operations. And what can we do with these policies? Well, we can, for instance, ensure IO fairness across different jobs. So we can ensure that even when we have different jobs accessing a shared storage resource, we can equally distribute the storage bandwidth across these, but also we can provide other types of quality of service. For instance, we can prioritize some jobs over others. So we want some deep learning workload to end the training stage faster, and we want to provide it more storage bandwidth to read the data set faster. We can give this specific job higher storage bandwidth with a given policy. These policies are implemented through control algorithms. These control algorithms receive IO metrics from the data plane stages, and with these metrics, the algorithms compute enforcement rules. These rules are sent to the data plane stage and are enforced at the data plane stage for each application. Of course, we are talking about these algorithms will receive metrics from the cluster. We are talking about supercomputers that can have thousands of compute nodes and thousands of jobs. So we need to have a control plane that is scalable. And the way we do to achieve this is to have a distributed architecture composed by both local controllers and global controllers. The local controllers are deployed at each compute node. These local controllers aggregate metrics at the level of compute node that take decisions at the level of compute nodes. But when we need to do coordination across data plane stages residing on different compute nodes, this decision needs to be done by a global controller, and that's why we need to have this hierarchical architecture. This component is also implemented as a prototype called Shepherd, and with Shepherd and Paddle, we have our control plane and data plane. And now just to give you a brief example on why this is useful, we have tested our solutions in different use cases. One of the use cases is aims at controlling metadata bursts at the Lustre file system. And another one aims at ensuring QoS across the distinct TensorFlow jobs running and sharing a given storage resource. I'm going to talk about the second one, but below this slide, you have the references for the two papers that describe better each of these use cases. And now going to this second use case. So let's assume in this figure, what I'm showing is we have 4 TensorFlow instances that are doing a training task, are training a model. These instances start at distinct times, and all these instances are sharing the same disk, so are reading the data sets from the same disk, and the disk bandwidth is limited to 1 GB per second. And if we, so this figure shows the scenario where we don't have any control and we just leave the TensorFlow instances run. And as you can see, what happens is, since these are running on a compute node and the disk as a scheduler at the operating system level, what the scheduler is doing is being fair. And for instance, in instant 4 that I'm highlighting here, we see that the 4 TensorFlow instances are running, and the bandwidth of the disk is more or less being shared, is equally being shared across this. But now let's assume we want a scenario where we want these instances to run, to have different bandwidths. So we want different QoS levels for these instances. So we want instance 4 to have 350 megabytes per second, instance 3 to have 300, 2 to have 200 megabytes per second, and instance 1 to have 150 megabytes per second. We can do this again with a baseline scenario without doing anything. So in this figure I'm showing, the problem is that on instance 4 and 5, what we see is that instances 4 and 3 are not complying with all the QoS goals we had for them. And on instance 5, the same, this is also not happening for instance 4, okay? And how can we solve this? Well, with our solution, by applying our solution and applying these QoS goals, we can see a different figure, okay? So this figure, what this figure shows is that now we still have the 4 TensorFlow instances running, but at step 4 and 5 of our training phase, we see that the instances 1, 2, 3, and 4 are being supplied with a storage bandwidth requested by the QoS goals, and the same is happening at step 5. So this is an interesting aspect. So through the prototypes I mentioned previously, we are able to provide these QoS goals. And also there's an important aspect here is that if you note, when we don't have the full disk bandwidth being used, for instance, on steps 1, 2, or 3, 6, and 7, we are providing the leftover bandwidth of the disk to the remaining TensorFlow instances, so this can train faster. And these are two important aspects of our solution. And so this concludes my overview of the storage solution of BigHPC. Of course, if you have any questions, I'm free to reply. Thank you.
Okay, thank you, João. And now we can go to the platform integration, where I can ask for Samuel intervention to explain how we did the integration of the different components. I'm having trouble here. Okay, I think you can control now, Samuel.
Let me check. Hope you can hear me.
I can hear you, yes, Samuel.
Okay. Yes, so I can manage this. So hello, everyone. So here we'll focus on the integration activity for the BigHPC platform. Our goal here was to get everything together and deploy it on real infrastructures, all the components that were presented before. Summarizing what have been detailed before, we can group all the component units over two groups. One group of services, that is the first one that I represent here in the first column. This one is the one that we deployed on Kubernetes cluster. And then a second one that is about the local applications that run inside the jobs that will be part of that will be running on the compute node. So our first step was to understand what was the required workflow to start working and bring everything together. So the first step was to define the required test beds. So we review that there is the details related to the environment for the developers themselves. And on that regard, we prepare the development test bed. The development test bed, it works over virtual machines or also over the Kubernetes cluster. And it allows for the first phase of the development and testing the integrations. Then we also need the preview test bed, where this preview test bed provides the real infrastructure for the software itself. And of course, in the end, the idea is that we can deliver a release of that software that is ready to go to the production infrastructure. Looking to the methodology that we adopted, so we focus on the DevOps methodology. On that regard, we try to bring to this project some ideas like continuous development, continuous delivery, continuous deployment, and all of that kind of practices. And we start working on that over the GitLab platform. Using the GitLab platform, the normal flow that we used was to start from an issue, then someone starts to code and open a merge request for that requirements, and then the tests that I will explain afterwards work automatically from a pipeline definition. And in the end, we have the validation from the responsibles that develop those code, and we can get the release. So the idea was quite simple. So we prepared some templates. Those templates define pipelines over GitLab, and that pipelines allows to run all the required tools to do all the quality software validation and also do the security checks, both provided from the developers and also from the operators from the infrastructure management. This also provides a way to get the report, so we can also check everything that happened during that quality assurance validation. We can look to the linting, the coverage, the security results, the unit testing, and that can be accessible from each job that just validated that software. In this case, the components for the BigHPC platform. But then this is not only about the software, it's also to bring all this software into the real infrastructure. And on that regard, the continuous cycle and the automation is harder. And that's what we bring here also. So we start to look into the requirements for testing, validation, and delivery for the software, as I explained before. But then we also need to deploy this into the real infrastructure and just to deliver this in a way that doesn't corrupt the security, doesn't bring more requirements, and that turns easier for those that want to adopt this solution. So going over the three phases. So the first one that I start to explain before is just the first phase, where we just start to test the software, run the tools that are required, do all the testing, also go further to the system testing over the real infrastructure, and then we can just approve the merge request for the final release that can be deployed. Then we go to another complex operation, that is to bring all of this software into the real infrastructure. On that regard, here we have a different approach. So we also go to the same ideas, but with a different pattern. So now we focus on the deployment. We follow the GitOps pattern using the pull mode that just goes to check all the configurations in a repository, a Git repository, and this allows to manage all the state and all the configurations and all the services from a single point of state. And it allows several interesting features like rollback, recover, backup, and all of this stuff, all supported by Argo CD and using Kubernetes features that the Kubernetes platforms also provides. So just giving the big picture of the final pilot that we prepared. The main idea here is that we can, using GitOps, we can protect the access from the developers and the users outside to the real infrastructure. So the operators can just adopt the code that has been already validated by their own testing, and it can be integrated in those infrastructures. And they can just be selective and just adopt what they want. All that code are being continuously managed and tested. And so we can also analyze, just like I explained in the previous slide, and always get the feedback to the developers so they can just do the required improvements to achieve the desired state. Also, we go ahead. So in terms of these integration activities, we try also to turn easier for the users and also for administrators, the management of all that tools. So as presented before, we have all the code, all the comments and everything like that, but you want to turn this easier to understand. So you also provide some interfaces and views that allows the better user-friendly approach for someone that wants to start to, for example, here some examples, to upload images to the virtualization manager, to submit the BigHPC job, or also to configure the BigHPC platform, for example, to configure a BigHPC partition with all the details that we mentioned before. So this is just the quick summary for all the integration activity. And now I can pass the word to Bruno again.
Sorry. Okay. Thank you, Samuel. And we can now go to the main results and takeaways that we can that we made from this BigHPC project. So as we already mentioned throughout the presentation, there were several prototypes developed and along the project duration. PIO, the virtualization manager, and the monitoring probe in 2021, the container architecture in 2022, and Shepherd and Paddle in 2023. And here is the list of the publications that were the outcomes of this project. There have been a lot of publications. You can also consult them in the web page. And finally, the main takeaways. So the BigHPC project developed a unified framework for running parallel and big data jobs at HPC centers. This is resourcing to containers for easier portability and deployment, while implementing storage QoS policies to ensure fairness and avoid I/O bottlenecks. We already saw these two takeaways. Why a container-based solution? Because it's easier for users to deploy, and the importance of the QoS policies. I think it's also been detailed throughout the document, throughout the webinar, why it is important. And also finally, having a tool to monitor and visualize the cluster's usage, both in real time and also off record, but afterwards when we need to interpret the data that we gather. So this is our presentation for today, and we are now open to questions that you would like to ask all the presentators. Thank you, everyone.
Okay. Thank you, Bruno, João, Samuel, and John, for your very interesting presentation. I would like now to see if everyone has any questions. Don't see any questions in the chat, so I can start with some of them. So my first question would be basically to generate a discussion here between all speakers. And so what's the next step? So basically when the project started, so probably 3 years ago, in these 3 years, there was a lot of changes in this research topic. And I would like to first understand if after 3 years, these requirements are still complying with the original ones, and what are the next steps? So for the exascale computing and that kind of stuff.
I don't know which one would like to take the question. I think.
I'll take a stab at it. So I would say, as compared to 3 years ago, the machine learning workloads are more important than ever. They have grown quite a bit. We've seen this at our center. How efficiently they run, how easily they run is pretty much based now, I think, completely on containers. And I'd say having access to multiple HPC resources that can support the different ML workflows and making it easier for our users to figure out how to run them and implement them, because I know our users kind of struggle with this and they're still figuring out how to put this in their scientific simulation workflows. And now we have a whole new group of users who are sort of pure computer scientists who are just doing machine learning. And we have a lot of exciting new architectures out. There are new GPUs from NVIDIA, AMD, and Intel, hopefully, finally, will get theirs out. And so our users don't want to learn the sort of geeky stuff that I enjoy, like the details of each piece of hardware. They just want to bring their workflow somewhere and run it and get results. And that's where I think this is headed, right? An easy way for them to do that, especially if we have container repositories for solution for each architecture, and we have access to a variety of resources that they can deploy it on.
Okay, I agree, João. Thank you.
I can add something from the perspective of storage systems. I think that when we started this problem of ensuring quality of service and avoiding the saturation of parallel file systems was important, but as supercomputers grow in terms of the number of available resources for computing, so the number of compute nodes is increasing, the supercomputers are getting bigger, but the technology used to support the data for the jobs running on these compute nodes is not improving a lot. At least the design and the implementation of these parallel file systems, it's pretty much the same. And so what we can expect is, if we have more compute nodes and more jobs doing I/O to a shared storage parallel file system, these will break more often. So I think that it's still relevant, if not more relevant now, to have solutions that can avoid this saturation and making the whole cluster unavailable, and so users cannot use it if they can't access their data.
Okay. Okay, so we have a question from Christian German. So, how to manage a preemption on planning of global controller? So I think Christian is referring to the global controller from storage.
Christian, can you give a bit more of can you highlight a bit more the question? So preemption in terms of what?
Preemption in terms of being the first to run my jobs.
Be the first.
There's
So
many jobs in the queue, and you want to jump to run your job first.
So you, if I understand your question, so you want to know how the global controller can make jobs run first than others? Is that
Yes.
it?
Yes.
Yeah, that's yeah. Go ahead, João.
So that's us. Go ahead, Ahmed.
Yeah,
So if a user has submitted a workload and it has not been scheduled yet, so it's easy to delete the workload just with the delete command. But if the job is running, it's extremely difficult for us to preempt the resources and get back to the queue. So probably the job will run, and we don't want the resources to hang in a state where you cannot control back all other jobs, or you cannot run the other jobs efficiently. So right now there is no way if the job is running, but if it has not been run or it has not been scheduled yet, it's quite easy. You can just submit a request to delete the job and it will not be scheduled at a later point of time. So did I answer your question? Thank you.
Okay, I have another question in the meantime. And so Samuel, is this for the deployment part? So do you think this pipeline and this testing methodology that you created, do you think this will help other centers if they, let's say they want to use the BigHPC prototypes that we have created here and apply them to their centers as well?
Yes, of course. Thank you for the question, Ricardo. Using this methodology, everyone can easily start to adapt this platform solution, since they can just easily integrate their own tools, their validation tools, and everything they need to in their own infrastructures, and start to check all the software and everything that we produce here during this project. Also, it allows and provides deployment recipes that easily allows to deploy on any infrastructure that needs to start working with our solution.
Okay, perfect. Does anyone has any other question or comment? No. Okay, so let me just share my screen here. Okay, so thank you for your participation, your question, and it's time to close our webinar. Please stay tuned in our communication channels for these final steps of the project. And thank you very much for joining us. And I would like to thank again João, Bruno, John, Amit, and Stephen for leading this insightful discussion. Okay, thank you very much to you all.
Thank you.
All right, thank you.
Thank you.
Bye.